Similar to the elevator project, the logic circuits, unfortunately, may or may not be physically something that you can build at home. So we're going to also do this, well, I'm going to do this in LTSpice and see if LTSpice makes sense. I'm also going to do a second section where I do the same circuit that we made in section 3 and create it in Tinkercad, which may or may not lead into some playing with Arduino as an automated testing system, just for the fun of it. One thing that may cause problems is the 1.5 volt outputs that we were getting because we were using the red LEDs that only require 1.5 volt. So in the case of the AND gate, you would get a 1.5 volt high and a 0.7, 0.8, 0.5 volt, depending on the diode, low, which those voltages are not only not very different from each other. I believe the low is low enough to pretty much register as a low on any input, but the 1.5 volts may not be high enough to be at the minimum for the digital inputs of something like an Arduino or a Raspberry Pi to actually recognize it as an active high. Very often you want at least 2.5 volts in a 5 volt system to be definitely considered to be a logic high at the input. We can get by this in a number of ways. We can get by this by using an LED with a larger voltage drop. We can gang voltage drops, maybe multiple LEDs in series, or we can do some calculations based on the current that will be flowing through the LED and insert a second resistor in series with the LED that will create a voltage drop of, let's say we wanted to use a red LED still. Ideally, we want this 1.5 volts to rise to very close to 5 volts. So we want to add 3.5 volts. So we would choose a resistor that in this series circuit would result in this output being lifted to the 1.5 volts of the LED plus 3.5 volts voltage drop across an appropriately sized resistor. Let's play. Also, I'm going to note that at this point, this is activity 3 related, and this is probably at the point where you don't need me doing a continuous narration of what I'm doing on the screen in LTSpice or in Tinkercad. So I'm going to just mute my audio and probably speed up the video in fairly boring areas, and then slow it down at specific points where it makes sense for me to talk about what is on the screen. Alright, let's do some initial tests. The first being whether or not it works. The second being what voltage we get out at the outputs based on what we connect the inputs to. So let's begin with OR. Oh no, let's do it all. So we'll initially connect let's do it all. So we'll initially connect everything to 0 volts. And simulate, edit, DC operating point, OK, pop it there, and as usual I'm forgetting a ground. So let's put the ground right there. So now that we've run it once, I'm not even going to look at these right now. I'm going to add some voltages based on the simulation. Alright, so initially with 0 or 0, we are getting 0.03 volts. Is that volts or an F? Okay, so actually the voltage at OR Z, V OR Z, is 2.9 to the minus 17th, which well, that's pretty neat. I had to look it up, but 2.92 to the minus 17th is basically 29 attovolts. ATTO. So basically 0. So low in, low in, low in, or low in is low out. Low and low is also low, but in this case we have 0.6 volts. And if we look at Y, we can see that the current through the LED for the AND gate is only 19 microamps, while the current through the input diodes for A and B are each passing 428 microamps. So in this case, the current through the resistor for the AND gate is being split evenly between the two input diodes for the AND gate, and barely anything is passing through the LED. So this voltage drop, the 0.6 voltage drop that we're seeing here, is the 0.6 volts across these two diodes. And finally, if we go to the NOT gate, the NOT gate is connected low, the transistor is not conducting, all current is passing through the resistor, and the LED is being held at 2.56 volts. with a current of 480 microvolts. Sorry, 480 microamps, which matches the current through the collector resistor. This is good to know for a number of reasons, not the least of which is that this LED has a voltage drop of about 2.5 volts, which is usually enough for any standard 5 volt input to consider it a high. We can work with this. Now, if one or the other input on the OR gate is high, then the output should go high. So delete one, reconnect to 5 volts, and simulate. With a 1 and a 0, our output is a 1, 4.4 volts. I don't really need to switch these inputs to prove that this 1 and this 0 would give you the same result, so instead we are just going to put both high and verify that that works. And our OR gate works just fine. The AND gate. We know that 0 and 0 equals 0.6 volts, which is close to a 0. It's not as good as I'd like it to be, but it is what it is with simple diode logic. If we put one of these high, same result, 0.6 volts, and we're still low. High and high should give us a high. And once again, we're getting a high of 2.56 volts, which is the voltage drop across this LED at the current passing through it. Very slightly different from the NOT gate, but not enough to matter. And finally, with the NOT gate, 0 becomes 2.6 volts, while a high should drop us close to 0. And 90 millivolts is definitely a 0. And before we move on to doing the same thing in Tinkercad, we're going to also simulate what we did in the physical circuit where the output of the OR was tied to the NOT gate. So delete the NOT, and we'll run a jumper wide and obvious from the NOT gate to the output. With the OR gate both tied to high, we have an output that's high, which means that the output of the NOT gate should be a low. Which it is, slightly higher than the 90 millivolts when directly connected to 5 volts because of the diode drops here, but it's exactly what we were expecting. Now the big question is, if I chop that and bring it low, The output of the OR gate has gone low with a 37 microvolt output, which of course is not going to be able to turn on an NPN transistor, the 0.7 volt drop requirement here, and we go high. And in the process, we've successfully simulated a NOR gate. Now, before we move on, I just had an idea, and I don't know if this is going to work, so this video may or may not even make it to you. If it does, it might be interesting from a number of standpoints. Something that is maybe not possible in Tinkercad, but is possible in LT-Spice if we change the inputs and the simulation function, is to watch the dynamic response of the output to changing inputs. We can really only watch the voltage. We can't watch the LEDs light up, and there's no buttons to press, but we can certainly watch the output voltage relative to the input voltages. Now, the easiest case is the NOT gate, because it has one input and one output. So it's fairly straightforward to just delete this, tying it to the OR gate, add a voltage source, and rather than a DC value, I'm thinking about a pulse, but I'm going to go simple with what we already know and do a sine with a plus 2.5 offset, a 2.5 amplitude, and a frequency of just 1 hertz. It's fine. And move this voltage to show the input voltage and connect the AC supply. And then run a transient simulation for a few cycles. Simulate. Delete this. And we will change that to a transient analysis with, say, 3 cycles. So with a frequency of 1 hertz, 3 cycles is 3 seconds. Now if we simulate this, this should be interesting. And look at the input voltage versus the output voltage. So with this circuit, we are in fact getting something square-like with a transition that begins at about 1.8 volts and is fairly complete by 0.7 volts. So from 0.7 volts to 1.8, you would not want to trust this as an actual NOT gate. But outside that transition region, where the transistor is actually amplifying the variation to the input, you would just want to stay away from that. But outside that range, not bad. If you're okay with a maximum of 2.5 volts as a high. The OR gates and the AND gates are a little more complex in that with 2 inputs you have 4 combinations that need to be tested. Now you could cheap out and do a single source to a single input and just tie the other input to either 5 volts or 0 volts and do a simulation of both. But what I'm thinking is that if I set up two sine waves that are 90 degrees out of phase, I would get essentially a quadrature encoder input that would cover low, 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 high, 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 low, back to low, low on a 1 Hertz cycle. So let's try that. That's very interesting. So let's say we establish a criteria for a high as anything above 2.5 volts. The OR gate is above 2.5 volts when one input or the other input are above about 3 volts. This little dip in the middle is problematic, possibly, but basically it works. And let's try this with the AND gate. And simulate. A is green, B is blue, and the output of A and B is red. So now, what do we have? In the case of the AND gate, at present, we are still only using the LED's voltage drop, not the resistor that I mentioned earlier, to bring up the input voltage from the 2.6 volts. So high is considered to be 2.56 volts. So for now, if we take an arbitrary condition of if the output is above 2 volts, which keeps us away from this little knock when it's low, and gives us a little half volt headroom on the high. If we call it high above 2 volts and below 2 volts is low, then it goes high when the minimum voltage on both is above about 1.25 volts. So you can see that B is definitely above 2.5 volts, but it doesn't actually make the output rise above 2 volts until B is above 2 volts and A is above 1.25-ish. It then stays high until B, that was highest first, drops below the 1.25 volts, followed by A also dropping below 2.5 volts. But again, we have this very interesting little knock at the crossover point. And the range between this crossover point and a high is only 1.15 volts. So that would be difficult to make. It would be difficult to make anything even reasonably complicated with. Now, just for fun, again, if we take away the NOT gate and its input, and instead the NOT gate's input will be the output of the OR gate. This should be very interesting. Simulate, and we look at the input and click a second time. Input A, input B, and not Z, which effectively is the output of a NAND gate. Sorry, a NOR gate. So it should be the opposite of OR. And looking at the cycle, we can see that the output is high until one or both of the OR inputs goes above 1.4 volts and then begins rapidly dropping towards 0, stays 0 until the voltages at input A and input B both drop below 2 volts. So there's a little bit of yeah. And if we add on the output of the OR gate to add some interest to this, then we see that input A to the OR gate, input B to the OR gate results in output Z of the OR gate driving the input of the NOT gate high when the output drops below about 1.7 volts. It's rather pretty. You would not want to make a computer out of this, though. Now let's move on to Tinkercad. Once again, there's going to be limited audio on this. I'm going to quickly build the circuit and then we'll play. Okay. So yeah, let's try these slide switches. So I'm just going to leave that there. And bring that down there. So this will be input A, this will be input B. To the left will be a low connected to ground, and to the right will be a high connected to 5 volts. So here is 5 volts and 5 volts. Here is, ignore the plus and minus, I didn't notice those very faint markings until just now. The top rail is going to be positive and the bottom rail is going to be negative. So negative to there and negative to there, which makes the middle terminal for diode A and the middle terminal for diode B. And let's color code this. so it's not confusing. So that's going to be negative. That's going to be, I can only do one at a time. All right. Black. Black. Oop. I had just realized that's incorrect. So, if we start the simulation, we should initially have a 0 and a 0 and a 0, a 0, a 0, a 0, a 0, and a 1. So one LED on. Oh, yes, and yeah, I forgot, we need a power supply. Whether it's an Arduino or a battery, it doesn't really matter, but we'll go with an actual 5-volt power supply because this is 9 volts and we want everything to be essentially the same. Start simulation. So 5 volts up to 5 amps. Right now our circuit is drawing 627 microamps with one LED on the NOT gate. 0 in, 0 volts in is a low, inverted to a high. If we connect it to the 5 volts by clicking the slide switch, our high becomes a low. OR gate, low, low, low. One high is a high, both high is a high, the other low works. AND gate, low and low, low, high and low, high and high, doesn't work. Aha, I see. The AND gate resistor is also tied to 5 volts. Low and low is low, high and high is high, either one being low is low. Sweet, that works. Well, now this is interesting because it seems connecting the voltmeter is preventing the LED from turning on. And that is incorrect. That should not happen. Somehow, I've created a short circuit. The circuit is supposedly drawing 5 amps, and so the voltage has dropped to 737 millivolts. But that doesn't make any sense. That makes sense. That makes a lot of sense. Yeah, I did that wrong. So although the circuit worked logically, it created a short circuit, and the short circuit is the reason it looked like it was working just fine. So now on the AND gate, 0 and 0 is 0, 0 and 1 is 0, 1 and 1 is 0, but we're only at 1.25 milliamps. And we are not short-circuiting anything. And now, if we try and read the output voltage, one point 8 volts on, 39 millivolts when low. That's a lot better. And that is a perfect example of why I tend to set current limits in the real world on power supplies when I'm first turning on a test circuit. That wouldn't have happened. Typically, I would have set this to 100 milliamps instead of allowing the power supply to drop 5 amps through the breadboard, which I guarantee you right now in the lab would cause melted plastic and a nasty smoky smell. Check, double check, and take precautions.